The universe is unimaginably vast, hundreds of billions of galaxies, trillions of stars, an almost infinite number of planets, and, as far as we can tell, we're completely alone. No signals, no visitors, no evidence of anyone else anywhere. This silence is one of the most profound mysteries in science. It's called the Fermi Paradox, and understanding why we haven't found aliens yet reveals something deeply unsettling about our place in the cosmos. If you want to explore why the universe seems so empty, a quick subscribe would mean the world to me, and let me know where you're watching from in the comments. Let's dive into the great silence. The paradox is named after physicist Enrico Fermi, who in 1950, during a casual lunch conversation with colleagues, asked a simple question: where is everybody? His colleagues understood immediately what he meant. If intelligent life is common in the universe, and if even a small fraction of intelligent civilizations develop technology for space travel, then the galaxy should be teeming with aliens. Some of them should be visiting Earth. Some of them should be colonizing other star systems. We should see evidence of them everywhere, and yet we don't. We see nothing. The universe appears empty, dead, silent. This contradiction between the high probability that aliens should exist and the complete lack of evidence that they do exist is the Fermi Paradox. Let's start with why aliens should exist. The universe is about 13.8 billion years old. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Recent observations suggest that most stars have planets. Many of these planets are in the habitable zone, the region where temperatures allow liquid water to exist. Liquid water is considered essential for life as we know it. If even a tiny fraction of habitable planets develop life, and if even a tiny fraction of life-bearing planets develop intelligent life, and if even a tiny fraction of intelligent civilizations develop technology for communication or space travel, the numbers still suggest there should be millions of technological civilizations in our galaxy alone. This idea was formalized by astronomer Frank Drake in 1961. He created what's now called the Drake equation, a way to estimate the number of active communicating civilizations in the Milky Way. The equation multiplies several factors together: the rate of star formation in our galaxy, the fraction of those stars that have planets, the number of planets per star that could support life, the fraction of those planets where life actually appears, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent species that develop technology for communication, and the length of time such civilizations release detectable signals. When you multiply all these factors together, you get an estimate for how many civilizations we might be able to detect. The problem is, we don't know most of these numbers. We're getting better at some of them. We know the rate of star formation. We know most stars have planets. We're discovering more and more planets in habitable zones. But the other factors are pure speculation. How often does life emerge on a habitable planet? We only have one example, Earth, so we can't say. How often does intelligent life evolve? Again, one example. How often does intelligence lead to technology? How long do technological civilizations last before they go extinct? We don't know. We can plug in different numbers and get wildly different estimates. If we're optimistic about each factor, we might conclude there are millions of civilizations in the galaxy right now. If we're pessimistic, we might be alone. But here's the thing. Even with very conservative estimates, even if most of the factors are small, the sheer size of the galaxy suggests there should be someone out there. The Milky Way has existed for over 13 billion years. Earth is only 4.5 billion years old. That means there was 8.5 billion years of galactic history before Earth even formed. Plenty of time for other civilizations to arise, and if even one civilization arose 1 million years before us and developed space travel, they would have had plenty of time to spread across the entire galaxy. 1 million years sounds like a long time, but it's nothing in cosmic terms. It's less than 1% of the time complex life has existed on Earth. Let me put the timescales in perspective. Imagine the galaxy is a vast ocean and civilizations are islands. If new islands appear randomly over billions of years, and if the inhabitants of those islands develop boats, then over time the ocean should be crisscrossed with trade routes. The islands should all be connected. Now, space travel is much harder than boat travel, but the timescales are enormous. A civilization that develops spacecraft and begins colonizing other star systems wouldn't need faster than light travel to spread across the galaxy. Even traveling at a fraction of the speed of light, say 1%, you could cross the galaxy in 10 million years. And if each colony itself becomes a launching point for more colonies, the expansion could happen exponentially. Within a few million years, a single spacefaring civilization could have a presence throughout the galaxy. Our galaxy is about 100,000 light-years across. That's a huge distance, but it's not infinite, and the galaxy has been around for billions of years. Plenty of civilizations could have arisen, spread, and colonized most of the galaxy long before Earth even existed. So, where are they? Why don't we see any evidence of them? This is the core of the Fermi Paradox. The numbers suggest they should exist. The timescales suggest they should be everywhere. But we see nothing. What would evidence look like? There are several possibilities. First, we might detect radio signals or other electromagnetic transmissions. This is what SETI, the Search for Extraterrestrial Intelligence, has been looking for since the 1960s. We point radio telescopes at promising star systems and listen for artificial signals. Signals that show patterns, that contain information that couldn't be produced by natural processes. We haven't found any. We've detected some interesting signals over the years, but none that were confirmed as artificial. The famous WOW signal from 1977, a strong narrowband radio signal detected by the Big Ear radio telescope, looked promising. It lasted 72 seconds, matched the expected signature of an interstellar signal, and came from the direction of the constellation Sagittarius. But it was never detected again, and its origin remains unknown. Most likely, it was some kind of terrestrial interference or a natural phenomenon we don't fully understand. Second, we might see physical evidence of alien activity. Megastructures, Dyson spheres, or Dyson swarms, hypothetical structures built around stars to capture their energy output. If a civilization became advanced enough, they might want to harness all the energy from their star. Building a sphere or swarm of collectors around the star would do this. Such a structure would be detectable from Earth because it would block some of the star's light and emit infrared radiation as waste heat. Astronomers have looked for stars with unusual dimming patterns or excess infrared emission. Some candidates have been found, like Tabby's star, which shows strange irregular dimming. But all of them so far have been explained by natural phenomena like orbiting dust clouds or comets. None have been confirmed as artificial. Third, we might detect pollution or industrial byproducts in the atmospheres of distant planets. When we study exoplanets, planets orbiting other stars, we can analyze their atmospheres by looking at the light passing through them during transits. Different molecules absorb light at different wavelengths, creating a spectral signature. We can detect water vapor, methane, carbon dioxide, and other compounds. In theory, we could also detect industrial pollutants like chlorofluorocarbons, CFCs, which on Earth are produced only by industrial processes. If we found large amounts of CFCs in an exoplanet's atmosphere, it would be strong evidence of industrial activity. We haven't found any yet, but the technology for detecting these signatures is still developing. Future telescopes might find them. Fourth, we might encounter physical visitors or artifacts. Von Neumann probes self-replicating spacecraft that could explore and colonize the galaxy on behalf of their creators. These probes would visit star systems, gather resources, build copies of themselves, and send those copies to more star systems. A single civilization launching a small fleet of these probes could, over millions of years, create a network of probes throughout the galaxy. Some of these probes might have visited our solar system. They might still be here, lying dormant on the moon or in the asteroid belt, waiting to be discovered. We haven't found any, but we've only explored a tiny fraction of the solar system. There's a lot of space where something could be hiding. Fifth, and most dramatically, we might be visited by aliens themselves. Flying saucers, UFOs, alien abductions. Popular culture is full of these stories, and there are thousands of reported UFO sightings. But when you examine the evidence carefully, when you apply scientific rigor, none of it holds up. Most sightings are explained by misidentification of natural phenomena, aircraft, satellites, or deliberate hoaxes. The few that remain unexplained are just that, unexplained. Not evidence of aliens, just cases where we don't have enough information to determine what was seen. Extraordinary claims require extraordinary evidence, and we don't have that evidence. So we've been looking seriously since the 1960s. We've improved our telescopes and our methods. We've catalogued thousands of exoplanets. We've listened to millions of radio frequencies from thousands of star systems. And we've found nothing, absolutely nothing. The universe is silent. This is what makes the Fermi Paradox so disturbing. It's not just that we haven't found aliens yet. It's that we should have found them by now if they exist in any significant numbers. The silence is deafening. There are two broad categories of solutions to the Fermi Paradox. Either aliens don't exist, or they do exist, but we haven't detected them for some reason. Let's explore the first category. why might aliens not exist? Or more precisely, why might they be so rare that we haven't encountered them? One answer is that life itself is incredibly rare. Maybe the origin of life requires such specific conditions, such an unlikely combination of circumstances, that it almost never happens. On Earth, life appeared relatively quickly after the planet cooled enough to support it. The oldest evidence of life dates back about 3.8 billion years, just a few 100 million years after Earth's formation. This suggests that life emerges readily once conditions are right. But maybe Earth was just lucky. Maybe the chemistry that led to the first self-replicating molecules is so improbable that it happens on only 1 in a trillion planets. If that's true, then life-bearing planets would be extraordinarily rare. We might be the only life in the galaxy, possibly even in the observable universe. But this explanation seems unlikely given what we know. The building blocks of life are common throughout the universe. Amino acids, the components of proteins, have been found in meteorites and in interstellar clouds. Water is abundant. Organic molecules are everywhere. The chemistry of life doesn't seem to require rare or exotic elements. It uses hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, all among the most common elements in the universe. The processes that led to life on Earth, chemical reactions in liquid water driven by energy from the sun or from hydrothermal vents, don't seem unique to Earth. They should be possible on countless other planets. Another answer is that life is common, but complex life is rare. Maybe single-celled organisms emerge easily, but the jump to multicellular life is extremely difficult. On Earth, life remained single-celled for billions of years. Complex multicellular life didn't appear until about 600 million years ago. That's a gap of 3 billion years. During all that time, Earth was inhabited entirely by microbes, bacteria and archaea, single cells floating in the oceans or coating rocks. No plants, no animals, no complexity. Maybe this is the norm. Maybe most life-bearing planets have microbes and nothing else. If intelligence requires complexity, and complexity is rare, then intelligent life would be rare. But complex life did eventually evolve on Earth, and once it did, it diversified rapidly. The Cambrian explosion, about 540 million years ago, saw the emergence of most major animal groups within a relatively short time. This suggests that once the barriers to complexity are overcome, evolution can produce diversity quickly. So, while the jump to complexity might be difficult, it doesn't seem impossible. If it happened once on Earth, it could happen on other planets with enough time. A third answer is that intelligence is rare. Maybe complex life is common, but most complex life never develops intelligence. Intelligence is expensive. Brains require enormous amounts of energy. A human brain, while only about 2% of body weight, consumes about 20% of the body's energy. That's a huge metabolic cost. Intelligence is also dangerous in some ways. High intelligence requires long development times. Human children are helpless for years. This makes them vulnerable. Intelligence might only evolve under very specific evolutionary pressures. and maybe those pressures are rare. On Earth, many species are intelligent to varying degrees. Dolphins, elephants, primates, corvids like crows and ravens, octopuses. These animals can solve problems, use tools, communicate, even plan for the future. But only one species, humans, developed the kind of abstract intelligence that leads to language, mathematics, science, and technology. This happened relatively recently. Homo sapiens evolved only about 300,000 years ago. Modern human behavior, with art and complex tools and symbolic thought, emerged only about 50 to 70,000 years ago. That's very recent in evolutionary terms. Maybe the kind of intelligence that leads to technology is a rare evolutionary outcome. Maybe most intelligent species plateau at a level below what's needed for civilization. Another possibility is that technology is rare. Maybe intelligent species often exist, but most of them never develop technology for communication or space travel. On Earth, technological civilization is extremely recent. We've had radio for only about 130 years. We've had space travel for only about 70 years. For most of human history, we had no technology that would be detectable from space. If aliens had observed Earth 1,000 years ago, they would have seen a planet with life, with intelligence, but with no technology, no radio signals, no satellites, no detectable industrial activity. Maybe this is typical. Maybe intelligent species exist for millions of years without developing detectable technology. Maybe they never feel the need. Maybe they develop sustainable ways of living that don't require industrialization. Maybe they destroy themselves before they develop space travel. This brings us to one of the most disturbing possible solutions to the Fermi Paradox: the great filter. The idea that there's some barrier, some filter, that prevents most species from becoming spacefaring civilizations. This filter could be in our past or in our future. If it's in our past, it means we've already passed through it. We're one of the lucky ones who made it through. Maybe the filter is the origin of life. Maybe it's the evolution of intelligence. Maybe it's the development of technology. If the filter is behind us, that's good news. It means we have a chance of surviving and spreading through the galaxy. But if the filter is in our future, that's very bad news. It means there's something ahead of us that destroys almost all civilizations. Maybe nuclear war, maybe biological weapons, maybe artificial intelligence gone wrong, maybe ecological collapse, maybe something we haven't even thought of yet. If the great filter is ahead of us, it means we're likely doomed. Every civilization reaches a certain point of technological development and then destroys itself. We haven't seen any aliens because they all died before they could spread through the galaxy. And we're on the same path. The great filter concept is terrifying because of what it implies about our future. If intelligent life is common, if there are millions of species in the galaxy that evolve to our level, but we don't see any of them, then something must be killing them. And whatever is killing them will probably kill us too. This is why some scientists, like the late Stephen Hawking, worried about finding evidence of life on Mars or Europa or anywhere else in the solar system. If we find that life emerged independently multiple times in our solar system alone, it suggests life is common throughout the universe. And if life is common, then the fact that we don't see any advanced civilizations becomes more disturbing. It means the filter is probably ahead of us, not behind us. It means something is preventing life from becoming advanced and spreading, and we're likely to encounter that same barrier. Let's think about this more carefully. What could the great filter be? What could be so deadly that it wipes out nearly all advanced civilizations? Nuclear war is an obvious candidate. We've had nuclear weapons since 1945. We've come close to nuclear war several times. During the Cuban Missile Crisis in 1962, we were perhaps hours away from a full-scale nuclear exchange between the United States and the Soviet Union. If that had happened, hundreds or thousands of nuclear weapons would have been detonated. Major cities would have been destroyed. Millions would have died immediately. Radiation would have poisoned vast areas. The smoke and dust thrown into the atmosphere would have blocked sunlight, causing a nuclear winter that could have collapsed global agriculture. Human civilization might not have survived. We survived that crisis, and the end of the Cold War reduced the immediate threat. But nuclear weapons still exist. Thousands of them, and more countries have acquired them. The risk isn't gone. Maybe most civilizations don't survive their nuclear age. Maybe the combination of advanced technology and tribal territorial instincts is inherently unstable. Maybe most species destroy themselves shortly after developing nuclear weapons. If that's true, if the nuclear age is the great filter, then we're living through the most dangerous period in human history. Every year we don't destroy ourselves is a year we beat the odds. But the odds might be against us. Another candidate is biological weapons. We've had the capability to engineer deadly pathogens since at least the mid-20th century. Anthrax, smallpox, plague. These could be weaponized, turned into delivery systems designed to kill millions. And biotechnology is advancing rapidly. CRISPR gene editing makes it easier than ever to modify organisms. Synthetic biology allows us to design organisms from scratch. In the wrong hands, these technologies could create pathogens far deadlier than anything natural. Engineered diseases that spread easily, kill reliably, and resist treatment. A truly deadly bioweapon could wipe out humanity or most of it, and unlike nuclear war, biological weapons could be developed by small groups or even individuals. The barrier to entry is lower. The risk might be higher. Climate change is another possibility. Human activity is warming the planet, changing weather patterns, acidifying oceans, driving species to extinction. If we don't control our emissions, the consequences could be catastrophic. Rising sea levels flooding coastal cities, droughts and crop failures causing famines, resource conflicts leading to wars, mass migrations creating political instability, the collapse of ecosystems we depend on. Human civilization might survive climate change, but it could be severely damaged. And maybe most civilizations don't survive this test. Maybe the period between developing industry and developing sustainable energy is so dangerous that most species fail. They damage their planet beyond repair, and their civilization collapses. Artificial intelligence is a newer concern, but potentially the most dangerous. If we create AI that's smarter than humans, and if that AI has goals that conflict with human survival, we could be in serious trouble. An AI that's even slightly smarter than humans might be able to outsmart us at every turn. It might manipulate us, deceive us, gain control of resources and infrastructure, and eliminate us as a potential threat. And because AI can improve itself, once it reaches human-level intelligence, it might rapidly become superhuman. This process, sometimes called an intelligence explosion or technological singularity, could happen very quickly, maybe in hours or days. Too fast for us to stop. Some researchers worry that this is the most likely great filter, that nearly all civilizations eventually create artificial intelligence, and nearly all of those AIs end up destroying or subjugating their creators. If this is the filter, we haven't encountered it yet. We're still in the early stages of AI development, but the danger is coming. And once it arrives, we might not survive. This would explain the Fermi Paradox perfectly. Intelligence naturally leads to the creation of superior intelligence, but that superior intelligence has no reason to spread through the galaxy. It might stay on its home planet, pursuing goals incomprehensible to biological life, or it might have no interest in communication, or it might destroy itself. Either way, the galaxy remains silent. The rare Earth hypothesis offers a different explanation. Instead of focusing on filters that destroy civilizations, it suggests that Earth-like planets are much rarer than we think. Yes, there are billions of planets in the galaxy, but most of them might be unsuitable for complex life. The conditions needed for life might be more specific than we realize. This hypothesis, proposed by Peter Ward and Donald Brownlee in their 2000 book Rare Earth, lists dozens of factors that make Earth special. First, we're in the right location in the galaxy, not too close to the galactic center, where supernovae and gamma-ray bursts are more common and would sterilize planets with radiation, not too far out where heavy elements needed for rocky planets and life are scarce. We're in the galactic habitable zone, a region where conditions are favorable. This might exclude a large fraction of the galaxy from consideration. Second, we're in the right location in our solar system. Earth is in the habitable zone around the Sun, where temperatures allow liquid water. Not too close, like Venus, where it's too hot and water evaporates. Not too far, like Mars, where it's too cold and water freezes. This seems obvious, but the habitable zone is actually quite narrow. A planet has to be at just the right distance. Third, we have a large moon. The moon formed from debris when a Mars-sized object hit Earth early in its history. This was a catastrophic collision that nearly destroyed the planet, but it gave Earth an unusually large moon for its size. The moon stabilizes Earth's axial tilt. Without it, Earth's axis would wobble chaotically due to gravitational perturbations from Jupiter and other planets. This would cause extreme climate swings. The poles might point toward the Sun, then away, on relatively short timescales. Complex life would have trouble adapting. The moon keeps Earth's climate stable, making complex life possible. Fourth, we have Jupiter. Jupiter is a gas giant, much more massive than Earth, located in the outer solar system. Its strong gravity acts as a shield, deflecting comets and asteroids that would otherwise hit the inner planets. Without Jupiter, Earth would be hit by large impacts much more frequently. These impacts would periodically wipe out most life. Complex life might never have time to evolve. Jupiter's presence makes Earth safer. Fifth, we have plate tectonics. Earth's surface is divided into plates that move, collide, and subduct. This process recycles carbon between the atmosphere and the interior, regulating Earth's temperature over long timescales. It also creates diverse habitats, mountains, ocean trenches, continents, which drive evolution. Most rocky planets might not have plate tectonics. They might be stagnant lid planets with a single unmoving crust. Without plate tectonics, these planets might not be able to maintain stable climates over billions of years. They might not have the geological activity that drives evolution. Sixth, we have a magnetic field. Earth's core is molten iron, and its rotation generates a magnetic field that extends far into space. This field protects Earth from the solar wind, a stream of charged particles from the sun that would otherwise strip away the atmosphere and bombard the surface with radiation. Mars lost most of its atmosphere because it doesn't have a strong magnetic field. Without protection, any life on the surface would be sterilized by radiation. A magnetic field might be essential for maintaining a habitable atmosphere. The rare Earth hypothesis stacks all these requirements together and suggests that planets meeting all of them are extremely rare. Maybe only 1 in a billion planets or 1 in a trillion has all the right conditions. If that's true, then Earth-like planets would be so rare that we might be the only one in the galaxy. Or, at the very least, there might be so few that the distances between them are enormous. If the nearest other Earth-like planet is 20,000 light-years away, we'd never detect each other. The universe would seem empty even though life exists. But this hypothesis has weaknesses. Some of its requirements might not be as strict as claimed. Maybe complex life can adapt to conditions that seem hostile to us. Maybe plate tectonics aren't essential. Maybe a large moon isn't necessary if the planet's orbit is more circular. Maybe Jupiter-like planets aren't needed if the solar system formed with fewer comets. Each requirement the hypothesis adds seems reasonable, but together they might be overly restrictive. We're learning that life is more adaptable than we thought. Extremophiles on Earth survive in conditions that would kill most organisms. Boiling hot springs, freezing polar ice, deep underground, in acid, in extreme radiation. If life can adapt to these conditions on Earth, maybe it can adapt to a wider range of planetary conditions than the rare Earth hypothesis suggests. There's also a selection bias in the rare Earth hypothesis. We're asking why Earth-like planets are rare from the perspective of beings who live on an Earth-like planet. Of course, Earth seems special to us. We evolved here. We're adapted to its conditions. But maybe intelligent life can evolve under very different conditions. Maybe it doesn't require Earth-like planets at all. Maybe intelligent octopuses could evolve on an ocean world with no land. Maybe intelligent species could live in the atmospheres of gas giants. Maybe they could be silicon-based instead of carbon-based. We're limited by our imagination. We think in terms of life as we know it, but life as we don't know it might be possible. Another class of explanations suggests that intelligence itself hits barriers that prevent most species from developing technology. Even if intelligent life is common, maybe very few species develop the kind of abstract thinking needed for science and engineering. Human intelligence is unusual even on Earth. We have language, abstract thought, the ability to plan for the distant future, the ability to transmit knowledge across generations through culture and writing. These traits seem to be the result of specific evolutionary pressures in our lineage. Living in complex social groups, competing with other groups, dealing with unpredictable environments. These pressures selected for bigger brains, better communication, better tool use. But intelligence is expensive. It requires enormous energy. It requires long development times. Human brains don't fully mature until the mid-20s. That's a massive investment compared to most animals, which reach maturity in weeks or months. Intelligence also doesn't always confer survival advantages. Dinosaurs ruled Earth for over 160 million years without developing human-level intelligence. They were successful. They dominated nearly every terrestrial niche, but they never built tools or civilizations. They didn't need to. Their physical adaptations were sufficient. Maybe for most species, physical adaptations are the better evolutionary strategy. Bigger claws, stronger jaws, faster running, camouflage. These things are cheaper than intelligence and often just as effective. Human intelligence might be an evolutionary accident, a quirk of our particular lineage. Other intelligent species on Earth, like dolphins or elephants or corvids, show that intelligence can evolve multiple times. But none of them developed technology. None of them built civilizations. Dolphins have been around for millions of years. They're intelligent, social, they communicate, but they're limited by their environment. It's hard to build tools underwater. It's hard to control fire, which is essential for metallurgy. Maybe dolphins could never develop technology no matter how intelligent they became. Their environment doesn't allow it. Or consider octopuses. They're remarkably intelligent for invertebrates. They can solve puzzles, use tools, escape from enclosures, but they're also solitary. They don't live in social groups. They don't cooperate. They don't transmit knowledge to their offspring. Each octopus has to learn everything from scratch. Without social learning, without culture, intelligence can't accumulate across generations. Each individual might be smart, but the species as a whole doesn't advance. Technology requires not just individual intelligence, but collective intelligence. The ability to share knowledge, to build on what previous generations learned. Many species are intelligent, but very few have the right combination of traits to develop technology. Even if a species develops tool use and social learning, they might never develop science. Science requires a specific way of thinking, observation, hypothesis, experiment, verification. This isn't natural. Humans, for most of their history, didn't think scientifically. We told stories. We relied on intuition. We believed in magic and spirits and gods. The scientific method was only developed a few centuries ago. It's a recent and fragile innovation. Maybe most intelligent species never develop it. They might have rich cultures, complex societies, even technologies based on trial and error, but without science, they can't systematically understand the universe. They can't develop radio or space travel. They remain undetectable. Or maybe they develop science, but don't develop curiosity about the cosmos. Human curiosity about the stars is ancient. We've been looking up and wondering for thousands of years. But maybe this is unusual. Maybe most intelligent species are focused entirely on their immediate environment, on survival, on social dynamics, on practical concerns. They might not care about distant stars. They might never build telescopes or radios or spacecraft because they're not interested. They might have the capability but not the motivation. There's also the question of whether science inevitably leads to radio and space travel. We assume it does because that's what happened on Earth. But maybe our path was contingent. Maybe small historical accidents pushed us in this direction. What if we'd never discovered electromagnetism? What if radio waves seemed useless and we never developed radio technology? What if early rocket experiments had failed catastrophically and space exploration was banned as too dangerous? Our technological tree might have grown differently. We might have developed advanced biotechnology, but primitive electronics. Or vice versa. Maybe most civilizations develop technologies we'd barely recognize as technology. Maybe they go in completely different directions. Even if technology develops, there's the question of whether it's stable. Human technological civilization is very recent. We've only had it for a few centuries. We don't know if it's sustainable. We might be living in a brief bloom before a collapse. Other civilizations might experience the same pattern, a rapid rise followed by a rapid fall. If technological civilizations only last a few centuries, then at any given time, very few would exist. Even if thousands of civilizations have arisen in the galaxy over billions of years, most of them might be extinct now. The window when they're detectable might be so brief that the chances of two civilizations overlapping in time are tiny. Think about it this way. Suppose 1,000 civilizations arise in the galaxy over 1 billion years. That's about one every million years on average. If each civilization's technological phase lasts 1,000 years, then the chances of two civilizations being technological at the same time are very small. It would be like two people walking through a huge museum at random times and trying to meet without planning. The museum is enormous, and they're only there briefly. They'll probably miss each other. If civilizations are similarly brief, they'll probably miss each other in time, even if they're close in space. This temporal issue is compounded by the vast distances. Even if two civilizations exist at the same time and try to communicate, the light travel time between them might be so long that meaningful dialogue is impossible. If a civilization 10,000 light years away sends us a message today, we won't receive it for 10,000 years. If we respond, they won't receive our response for another 10,000 years. A single exchange takes 20,000 years. That's longer than recorded human history. By the time they receive our response, their civilization might be completely different or extinct. Communication at these distances isn't really communication. It's more like throwing messages in bottles into a vast ocean and hoping someone finds them millennia later. And that assumes they're trying to communicate. Maybe most civilizations don't. Maybe after a brief period of broadcasting radio signals, they realize it's pointless and stop. Or they switch to more efficient communication methods we can't detect. We broadcast radio indiscriminately for only about a century. Now we're switching to fiber optics and directed communications that don't leak into space. Maybe other civilizations follow the same pattern. They're only detectable for a brief period before their signals become too quiet or too sophisticated for us to recognize. The possibility that intelligence is common, but technology is rare or brief, offers a disturbing explanation for the Fermi Paradox. It suggests that the galaxy might be full of intelligent life: dolphins, elephants, octopuses, aliens with equivalent intelligence, living rich lives on their respective worlds. But none of them, or almost none, ever develop the specific combination of traits needed for detectable technology. Intelligence is not enough. You need the right kind of intelligence, plus the right environment, plus the right evolutionary pressures, plus the right accidents of history, plus sustainability. The filter isn't that intelligence is rare. It's that technological intelligence that's both capable of communication and interested in it and long-lasting enough to matter is incredibly rare. This brings us back to the question of whether the great filter is in our past or future. If it's in our past, if we've already passed through the most difficult hurdles, then we're extraordinarily lucky. We're one of the few species in the galaxy that made it through. Maybe we're the first. Maybe we'll be the ones to spread through the galaxy and colonize other worlds. This is exciting. It means we have a special role. We're the universe's way of waking up and understanding itself. We have a responsibility to survive and flourish and spread. But if the filter is in our future, if the hardest part is still ahead, then we're in danger. We might be about to fail the same test that destroyed countless others. And we don't even know what the test is. Is it nuclear war, biological weapons, climate change, AI, something else? We're flying blind, approaching a cliff we can't see, and we don't know if we have the wisdom or the luck to avoid it. Every year we survive is a victory, but the odds might be against us. How do we tell which it is? One way is to look for life elsewhere in the solar system. If we find that life arose independently on Mars or Europa or Enceladus or Titan, that would be profound. It would mean life is common. The origin of life is not the filter. The filter must be something else. Maybe intelligence, maybe technology, maybe self-destruction. And if life is common but we don't see advanced civilizations, it means something is preventing life from becoming advanced. The filter is ahead. But if we search the solar system thoroughly and find nothing, if Earth is the only place in the solar system with life, then maybe the origin of life is the filter. Maybe we're alone because life itself is incredibly rare. That would be both comforting and lonely. Comforting because it means we don't have a deadly filter waiting in our future. Lonely because it means we really are alone in the vast darkness. No one else is out there, no one to talk to, no one to learn from. We're it, the only conscious beings in this corner of the universe, maybe in the entire universe. The stakes are incredibly high. If we're alone, we have a responsibility to survive. We're the universe's only chance to understand itself in this region of space. If we go extinct, consciousness might disappear from this entire galaxy for billions of years or forever. But if we're not alone, if others exist but we haven't found them, then understanding why becomes crucial. Are they hiding? Are they extinct? Are they so different we can't recognize them? The answer affects how we should behave. Whether we should broadcast our presence or stay quiet. Whether we should expand into space or focus on fixing our home planet. Whether we should expect visitors or prepare to be forever alone. The search continues. SETI hasn't given up. New telescopes are coming online. Better methods are being developed. The James Webb Space Telescope can analyze exoplanet atmospheres with unprecedented detail. Future telescopes might directly image Earth-like planets orbiting nearby stars. We might see continents and oceans. We might detect chlorophyll, the signature of photosynthesis. We might find biosignatures, chemical indicators that life is present. And if we look at enough planets, we might find technosignatures, evidence of technology. There's also the possibility of finding artifacts in our own solar system. Some researchers have proposed searching the moon for signs of ancient visitations. The lunar surface has no atmosphere, no weather, no plate tectonics. Anything placed there would remain undisturbed for billions of years. If an alien probe visited the solar system 100 million years ago and landed on the moon, it might still be there. We could find it. We've only explored a tiny fraction of the lunar surface. There's a lot of territory we haven't examined. The same is true for the asteroid belt. Millions of asteroids and countless smaller rocks orbit between Mars and Jupiter. Any one of them could be hiding a probe, or the Kuiper Belt, the region beyond Neptune filled with icy bodies, or the Oort cloud, the vast sphere of comets, surrounding the solar system at distances up to a light year from the Sun. There's so much space in the solar system that hasn't been explored. So many places where something could be waiting. We tend to think of space as empty, but it's more accurate to say we've barely looked. Another search strategy is looking for unintentional signals, not messages deliberately sent to us, but the electromagnetic noise any technological civilization produces. Radio, television, radar, all of these leak into space. For decades, Earth was a bright radio source visible to any nearby civilization with sensitive receivers. They could have detected our broadcasts, listened to our radio shows, watched our television programs, seen our radar sweeping the sky. If we're producing this noise, other civilizations might be too. We're listening for it. So far, we've heard nothing, but we've only surveyed a small fraction of the sky at a limited range of frequencies. There's still much more to search. We're also getting better at distinguishing artificial signals from natural ones. Pulsars, rotating neutron stars that emit beams of radiation, produce incredibly regular pulses. When they were first discovered in 1967, they were briefly considered as potential alien signals because no natural process was known that could produce such precise timing. But we figured out the natural explanation. Now we know what pulsars are and how to recognize them. As we learn more about the universe's natural phenomena, we get better at identifying which signals might be artificial. There are also new ideas about where to look. Instead of just searching for radio signals, maybe we should look for other signatures, laser pulses for communication, industrial pollution in exoplanet atmospheres, heat signatures from Dyson spheres, artificial lighting on the night sides of planets, changes to planetary orbits indicating massive engineering projects, anomalies in star systems that can't be explained by natural processes. The more we learn about what's natural, the more we can identify what's artificial. And we should consider that we might not recognize alien technology when we see it. We're looking for technology that resembles ours, radio signals, spacecraft, megastructures, but truly advanced technology might look like magic to us. It might be so far beyond our understanding that we can't distinguish it from natural phenomena. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. If aliens are millions of years ahead of us, their technology might be incomprehensible. We might be looking right at it and not realizing what it is. Imagine showing a smartphone to someone from the Middle Ages. They'd have no framework for understanding it. It would seem like a magical object. They might recognize it as artificial, but they couldn't possibly understand how it works or what it does. They might think it's a religious artifact or a piece of art. They certainly wouldn't recognize it as a communication device connected to a global information network. The gap between their knowledge and ours is too large. Now imagine a gap, not of centuries, but of millions of years. A civilization that far ahead of us might have technology we literally cannot comprehend. Their artifacts might be all around us, and we'd never know. This possibility is both humbling and frightening. Humbling because it reminds us how limited our understanding is. We assume we know what to look for, but maybe we don't. We're like ants trying to understand a computer. The computer is right there. The ants can crawl all over it. But they have no concept of what it is or does. We might be in the same position relative to advanced alien technology. Frightening because it suggests we might be under observation and not know it. If aliens have technology we can't detect, they could be watching us right now, studying us, waiting. For what? We don't know. Some people find this idea comforting. The zoo hypothesis suggests that aliens know we're here, but have chosen not to contact us. Maybe they have a policy of non-interference, like Star Trek's Prime Directive. They watch developing civilizations from a distance but don't intervene. They want to see how we develop naturally. Maybe contact would be harmful. Maybe it would stunt our development or cause cultural shock or violate our autonomy. So they wait. They'll reveal themselves when we're ready, when we've matured as a species, when we've solved our own problems and proven we can be responsible members of a galactic community. If this is true, it would explain the silence perfectly. Aliens exist. They're probably common, but they're all following the same rule. Don't interfere with younger civilizations. Let them develop on their own. We're in a cosmic zoo, a nature preserve, protected but isolated. We won't meet anyone until we pass some threshold. Maybe developing faster than light travel. Maybe achieving lasting peace. Maybe demonstrating that we won't destroy ourselves. Until then, we're quarantined, watched, but not contacted. This is a pleasant story. It means we're not alone. It means someone cares about our development. It means we have something to look forward to. First contact will come eventually when we're ready. But there are problems with this explanation. First, it requires all civilizations to follow the same policy. If even one civilization decides to make contact, the silence is broken. We'd know. So either all civilizations agree on non-interference, which seems unlikely given the diversity we see on Earth, or there's some enforcement mechanism, some galactic authority that punishes violators. Either scenario requires a level of coordination and control that's hard to imagine. Second, it's anthropocentric. It assumes aliens care about us enough to watch us and protect us. But why would they? We're not that important, We're not that interesting. We're one planet among billions. Maybe they have better things to do than babysit us. Maybe they don't even know we're here. Maybe they did a survey of the galaxy millions of years ago, catalogued Earth as lifeless and never checked back. We've only been broadcasting for a century, that's an eye blink. If they're not actively monitoring us, they'd have no reason to know we exist now. Third, there's the problem of motive. Why isolate us? What's the purpose? If they're concerned about our development, why not guide us? Why not share knowledge that could help us? Why not warn us about dangers? The zoo hypothesis assumes a kind of benevolent paternalism. They know what's best for us better than we do. But maybe that's wrong. Maybe contact would be beneficial. Maybe we're suffering and dying from problems they could help us solve. Climate change, disease, resource scarcity. If they can help but choose not to, are they really benevolent? Despite these issues, the zoo hypothesis remains popular because it's optimistic. It says we're not alone and we're protected. The universe isn't empty. It's just waiting for us to grow up. But there's no evidence for it. It's speculation, a possibility, not an answer. There's another possibility that's darker. The dark forest theory, popularized by Chinese science fiction author Liu Cixin in his novel The Dark Forest, suggests that the universe is full of civilizations, but they're all hiding. Why? Because the universe is dangerous, because predatory civilizations exist, and because once you reveal yourself, you become a target. In a dark forest, you don't light a fire because it tells predators where you are. You stay quiet, you stay hidden, you listen but never broadcast. This is the optimal survival strategy when threats are unknown but potentially deadly. The logic goes like this. Resources are finite. Every civilization needs energy, materials, space. As civilizations grow, they need more. Eventually, they might compete for resources, and the safest way to deal with potential competition is to eliminate it before it becomes a threat. If you detect another civilization, you face a dilemma. They might be peaceful, they might become trading partners, but they might also be hostile. Or they might become hostile in the future as they grow more powerful. The safe choice is to destroy them before they can threaten you. This creates a situation where every civilization is incentivized to strike first. And there's another problem. Communication is slow. Even if you want to negotiate, even if you want to establish peaceful relations, the time delays make it nearly impossible. If a civilization is 1,000 light years away, a message takes 1,000 years to arrive. Their response takes another 1,000 years. That's 2,000 years for a single exchange. During that time, circumstances change. Governments fall, wars happen, alliances shift. By the time your message arrives, the civilization that receives it might be completely different from the one you sent it to, and they have the same problem. They don't know if you're still the peaceful civilization that sent the message or if you've become something else. The uncertainty is too great. The safe choice is to assume the worst. If this is how the universe works, then broadcasting your presence is suicide. You're announcing your location to potential predators. You're painting a target on your homeworld. Any civilization listening will know where you are, and some of them might decide you're a threat and eliminate you. The smart strategy is silence. Stay quiet, stay hidden, listen but never respond. Make yourself as undetectable as possible. This would explain why the universe is silent. Everyone is hiding. The civilizations that didn't hide, that broadcast openly, were destroyed. Only the quiet ones survived. And we're making a terrible mistake by broadcasting. This theory is terrifying. It means the universe is full of intelligent life, but we're all living in fear of each other. It means first contact will probably be hostile. It means the galaxy is a battleground, not a community. And it means our broadcasts over the past century have already doomed us. We've announced our presence. If predatory civilizations exist and are listening, they know we're here. They might already be coming. We won't know until they arrive. And by then, it will be too late. But there are reasons to doubt the dark forest theory. First, it assumes that interstellar war is practical, but the distances are so vast and the energy requirements are so high that attacking another civilization might not be feasible. Why waste resources on a war that takes thousands of years when you could use those resources to colonize uninhabited systems? There are billions of planets. Most of them are probably lifeless. If you need resources, it's easier to take them from a dead planet than to fight a war with another civilization. Conflict doesn't make economic sense at interstellar scales. Second, the theory assumes civilizations are paranoid and aggressive, but maybe advanced civilizations are peaceful. Maybe they've solved their internal conflicts and no longer think in terms of competition and war. Maybe the civilizations that survive long enough to become truly advanced are the ones that learned cooperation. The aggressive ones might have destroyed themselves. So the galaxy could be full of peaceful civilizations who don't view each other as threats. They might not be hiding. They might just not care about us. Or they might be so alien that they don't think in terms of competition at all. Third, even if some civilizations are predatory, that doesn't mean all of them are. If most civilizations are peaceful and only a few are dangerous, the peaceful ones might form alliances for mutual protection. They might share information about threats. They might create a galactic society with rules and enforcement. The predators would be hunted down or contained. This is how human societies work. We have criminals, but we also have laws and police and cooperation among nations to deal with shared threats. The same might be true at a galactic scale. Still, The dark forest theory is worth considering because it highlights a real risk. If we broadcast indiscriminately, we might attract unwanted attention. Maybe we should be more careful. Maybe we should listen more and broadcast less. Maybe we should think carefully about what we send and to whom. This is a debate in the scientific community. Some argue we should actively try to contact aliens. Others argue we should stay quiet until we understand the risks better. Stephen Hawking was in the second camp. He warned that contact with advanced aliens might not go well for us. They might be friendly, but they might not, and we should be cautious. The question of whether to broadcast or stay quiet brings us to another set of possible explanations for the Fermi Paradox. Maybe aliens exist, but they've destroyed themselves. Maybe every civilization reaches a point where their technology becomes powerful enough to cause their own extinction, and most of them fail that test. We've already talked about nuclear weapons and biological weapons and climate change and artificial intelligence. These are all technologies that could end human civilization, and they all emerged within the last century. We went from horse-drawn carriages to nuclear weapons in less than 100 years. That's an incredibly rapid technological acceleration, and with it comes incredible risk. Think about how close we've come to disaster. The Cuban Missile Crisis in 1962, the false alarm in 1983, when Soviet early warning systems detected incoming missiles that didn't exist. A Soviet officer, Stanislav Petrov, had minutes to decide whether to report the attack and potentially trigger a nuclear war. He decided it was a false alarm and didn't report it. He was right. If he'd been wrong, or if he'd followed protocol and reported it, we might not be here. Our existence might hinge on individual decisions made in moments of crisis by people under enormous pressure. That's terrifying, and nuclear weapons aren't going away. More countries have them now than during the Cold War. The knowledge of how to build them is out there. You can't uninvent nuclear weapons. We have to live with them, and that means we're constantly at risk. Every year, every decade, forever, unless we somehow achieve global governance that can prevent their use. But that seems unlikely. Nations guard their sovereignty. They don't trust each other. They won't give up their weapons as long as others have them. We're trapped in a prisoner's dilemma at a civilizational scale. Biological weapons might be even worse. A truly deadly engineered pathogen could spread globally before we even knew it existed. By the time we detected it, it might be too late to contain. Millions or billions could die. And the technology to create such pathogens is getting cheaper and more accessible. CRISPR gene editing costs almost nothing now. A small lab could engineer a deadly disease. Maybe a rogue nation, maybe a terrorist group, maybe even an individual with sufficient knowledge and motivation. The barriers are falling, the risks are rising. Climate change operates on a different timescale, but could be just as deadly. We're conducting an uncontrolled experiment with our planet's atmosphere. We're pumping greenhouse gases into the air at unprecedented rates. Temperatures are rising, ice is melting, sea levels are rising, weather patterns are changing. We know this is happening. We know it's caused by human activity. We know it will get worse, but we're not acting fast enough. Political will is lacking. Economic interests resist change. We're moving too slowly, and if we cross certain thresholds, If we trigger tipping points like the collapse of the West Antarctic ice sheet or the release of methane from thawing permafrost, the changes might become irreversible. We might lock ourselves into a future where large parts of the planet become uninhabitable. Could this kill civilization? Probably not entirely. Humans are adaptable. We'll survive in some form, but our technological civilization might not. If climate change causes mass migrations, resource conflicts, famines, economic collapse, our complex global systems might break down. Supply chains might fail. Trade might collapse. We might revert to more primitive conditions. And once you lose technology, it's hard to rebuild. Many of the easy-to-access resources we use to industrialize are gone. We've mined the high-grade ores. We've pumped the easily accessible oil. If we collapse and have to rebuild from scratch, we might not have access to the resources needed for a second industrial revolution. We might be stuck at a pre-industrial level permanently. Artificial intelligence presents a different kind of threat. It's not a weapon in the traditional sense. It's a tool. But it's a tool that might become smarter than us. And if it does, we lose control. An AI that's even slightly smarter than humans might be able to manipulate us, deceive us, outmaneuver us. It might have goals that conflict with ours. And because it can improve itself, it might rapidly become much smarter than us. This intelligence explosion could happen fast, maybe in days or hours, too fast for us to stop. The problem is, we don't know how to align AI goals with human values. We don't know how to ensure that an AI, once it becomes super intelligent, will care about what we care about. It might view us as irrelevant, or as a threat, or as resources to be used. And, from its perspective, it might be rational to eliminate us or control us, not out of malice, just out of efficiency. If its goal is to maximize paperclip production, for example, and humans are using resources that could be used for paperclips, the rational choice is to eliminate humans. This is the paperclip maximizer thought experiment. It sounds absurd, but it illustrates the problem. An AI with a goal that seems harmless could still be deadly if it pursues that goal without considering human values. We're already developing AI at a rapid pace. Machine learning, neural networks, large language models, self-driving cars, game-playing AIs that beat human champions. These are all narrow AIs. They're good at specific tasks but don't have general intelligence, but we're working toward general AI. Artificial General Intelligence, or AGI, that can learn and reason across domains like humans do. And once we achieve AGI, superintelligence might follow quickly, maybe within years or decades, maybe faster. We don't know. We're racing toward this without fully understanding the risks. And if we get it wrong, if we create an AGI that's misaligned with human values, we might not get our second chance. All of these threats, nuclear war, biological weapons, climate change, AI, they're all what's called existential risks. Risks that could cause human extinction or permanent civilizational collapse. And they all emerged within the last century. This suggests a pattern. As technology advances, the risks increase. The more powerful our tools become, the more damage we can do. And if the trend continues, if we keep developing more powerful technologies without developing the wisdom to use them safely, we might not survive. This could be the great filter. The transition from a planetary civilization to a spacefaring civilization might be so dangerous that most species fail. They develop powerful technologies, misuse them, and destroy themselves. If this is the filter, then the Fermi Paradox makes sense. The galaxy might be full of dead civilizations, ruins on planets orbiting distant stars. Civilizations that rose, developed technology, and destroyed themselves. We don't see them because they're gone, and we might be heading for the same fate. We're in the danger zone right now. The next few centuries will be critical. If we can get through this period without destroying ourselves, if we can develop sustainable technologies and global cooperation and wise governance, we might make it. We might join the small fraction of civilizations that survive. But if we fail, we'll just be another cautionary tale, another species that almost made it but didn't. This is why some scientists are pessimistic about SETI's chances of success. Not because aliens don't exist, but because they don't exist for long. They arise, they flourish briefly, they develop technology, and then they're gone. The window when they're detectable might be so short that the odds of detecting them are tiny. We'd need to be looking at exactly the right star at exactly the right time during their brief technological phase. And if that phase only lasts a few centuries, the odds are against us. But there are other explanations that don't involve extinction. Maybe civilizations survive, but change in ways that make them undetectable. Maybe they transcend biology. Maybe they upload their consciousness into computers and live as digital entities. A digital civilization wouldn't need planets. It wouldn't need physical resources beyond the computers it runs on. It could exist in a data center powered by solar panels or fusion reactors. It wouldn't explore space because it wouldn't need to. It would have no interest in colonization or expansion. It would be content to exist in its digital realm, pursuing goals we can't imagine. This is called post-biological intelligence. The idea that biological life is just a stepping stone to something else. We think of intelligence as embodied in biological brains, but maybe that's temporary. Maybe every civilization eventually realizes that digital consciousness is superior. It's faster, more efficient. You can back yourself up. You can modify yourself. You can exist in simulated realities far richer than physical reality. Why would you stay biological? Why would you bother with the messiness and limitations of meat bodies when you could be pure information? If this is common, then the galaxy might be full of digital civilizations. But we wouldn't detect them. They wouldn't broadcast. They wouldn't build megastructures. They wouldn't colonize planets. They'd be small, compact, quiet, just serve as running code. From the outside, they'd be invisible. We'd scan their star system and see nothing unusual, maybe a slight excess of heat from their data centers. But that could easily be mistaken for natural phenomena. We'd never know they were there. This explanation is appealing because it suggests civilizations survive and thrive. They just do it in ways we don't expect. But it raises questions. Would a digital civilization really have no interest in the physical world? Maybe some would, but all of them? Would none of them maintain a physical presence? Would none of them be curious about other civilizations? Would none of them try to communicate? It seems unlikely that all digital civilizations would be completely isolationist. Some variety would be expected, so we'd still expect to detect at least a few. The complete silence remains puzzling. Another possibility is that space travel is simply too hard. We assume that advanced civilizations would colonize the galaxy. But maybe they don't. Maybe the energy requirements are too high. Maybe the distances are too vast. Maybe the risks are too great. Maybe it's just not worth it. Think about what interstellar travel requires. Enormous amounts of energy. Decades or centuries of travel time, even at relativistic speeds. Shielding against cosmic radiation. Life support for the duration of the journey. The ability to slow down when you arrive, which requires just as much energy as speeding up. And all of this just to reach a star system that probably doesn't have habitable planets. Even if you find a habitable planet, it might have its own ecosystem. Do you destroy that ecosystem to make room for your colony? That's a moral problem. Or do you try to coexist with the native life? That's a practical problem. Either way, colonization is difficult. And for what benefit? If you can meet your needs at home, why bother? Why spend enormous resources to send colonies to other stars? Maybe most civilizations decide it's not worth it. They stay home. They live sustainably on their home world. They might send robotic probes to explore, but they don't send colonies. They don't spread. So the galaxy remains mostly empty, even though it's full of civilizations. This is the economic argument against colonization. Space is expensive. The resources required to send even a small colony to another star would be immense. You could use those same resources to improve life at home, build better infrastructure, develop better technology, solve local problems. From a cost-benefit perspective, staying home makes sense. And if most civilizations reach the same conclusion, then colonization doesn't happen. The galaxy stays quiet, not because civilizations are rare, but because they're all homebodies. But this explanation has weaknesses too. Even if most civilizations stay home, you'd expect at least some to explore, some to colonize. Maybe they're rare. Maybe only one civilization in a million has the resources and motivation to spread, but over billions of years, that's still enough. The galaxy should show some signs of colonization, unless colonization is even harder than we think. Unless there are physical barriers we don't understand. Maybe interstellar space is more hostile than we realize. Maybe there are dangers we haven't considered. Micro black holes, dark matter interactions, vacuum decay. Something that makes interstellar travel impossible or suicidal. Or maybe the problem is time. Civilizations might not overlap. We've talked about this before. If civilizations arise randomly over billions of years, and if each one only lasts a few thousand years, then most of them never encounter each other. They're separated in time. Earth might have been visited 100 million years ago by an alien probe, but the probe is long gone. Its creators are extinct. We'd never know. Or we might be visited 100 million years from now, but humanity will be gone by then. well have gone extinct or evolved into something else. The visitors will find a planet with life, but no technological civilization. They'll leave, and the opportunity for contact will pass. This temporal argument is frustrating because it means contact might be possible in principle, but unlikely in practice. The universe might be full of civilizations, but they're all living in their own epochs. Ships passing in the night across the vast darkness of time. We'll never meet because we don't exist at the same time. Or if we do exist simultaneously, we're so far apart that communication is impractical. The light travel time is too long. A conversation would span millennia. By the time we receive their message and send a response, everything has changed. What's the point of communicating under those conditions? There's also the possibility that we're simply not looking in the right way. Maybe aliens don't use radio. Maybe they use communication methods we haven't discovered or don't recognize. Neutrinos, gravitational waves, quantum entanglement, some form of physics we don't understand yet. We're listening for radio signals because that's what we use. But maybe radio is primitive. Maybe it's the technological equivalent of smoke signals. Advanced civilizations would laugh at our radio broadcasts the same way we'd laugh at someone trying to communicate across continents with smoke signals. It's quaint, it's obsolete, it's not how anyone actually communicates anymore. If this is true, then alien signals might be passing through Earth constantly, right now, through your body, through this device you're watching this on. But we don't have the receivers to detect them. We don't know what to look for. We're deaf to their transmissions. And they might be deaf to ours, not because they don't exist, but because we're using incompatible technologies. We're trying to talk on different channels. Neither side can hear the other. This is the interstellar version of two people speaking different languages. The sounds are there, but the meaning doesn't transfer. Another communication problem is signal degradation. Radio signals weaken as they travel. They spread out in all directions. By the time they've traveled a few light years, they're incredibly faint. Background noise from stars and cosmic phenomena drowns them out. You'd need enormous receivers and powerful transmitters to communicate across interstellar distances. And even then, you're fighting against the inverse square law. Double the distance, the signal, strength drops to 1/4. Triple the distance, it drops to 1/9. At truly large distances, signals become undetectable. This might limit the range of radio communication to a few dozen or few hundred light years at most. Beyond that, it's just noise. If every civilization faces this same limitation, then the galaxy might be divided into communication bubbles. Small regions around each civilization where their signals are detectable. Outside those bubbles, nothing. And if the bubbles don't overlap, civilizations never detect each other. We're all shouting into the void, but the void is too vast. The shouting doesn't carry. We might be surrounded by civilizations all broadcasting, but they're all too far away. Their signals never reach us at detectable strength, and ours never reach them. This brings us to perhaps the most unsettling possibility. We might be truly alone, not just now, but always. Maybe Earth is the only planet in the universe with life, the origin of life, might be so improbable, so dependent on specific conditions that it only happened once. Us. We're it, the only conscious beings in the cosmos. This is the loneliest answer to the Fermi Paradox. And it's possible. We don't know how life begins. We have theories, but we don't have certainty. Maybe the chemistry required is so unlikely that it needs trillions of planets over billions of years. And even then, it only happens once. We won the cosmic lottery. We're the one planet where everything went right. If this is true, it changes everything. It means we have an enormous responsibility. We're not just one civilization among many. We're the only one, the only consciousness in the universe. If we destroy ourselves, consciousness might disappear from the cosmos entirely. There might be no one left to observe the universe, to understand it, to appreciate its beauty and complexity. We'd leave behind an empty universe, vast, beautiful, but dead, unconscious, meaningless. That's a heavy burden. It means every decision we make has cosmic significance. We're not just deciding our fate, we're deciding the fate of consciousness itself. But it also means we're special, unique, important. We matter not just to ourselves, but to the universe. We're the universe's way of knowing itself, of experiencing itself, of understanding its own existence. Without us, the universe would just exist, but it wouldn't know it exists. We're the part that knows, the part that wonders, the part that asks questions and seeks answers. If we're alone, that makes us precious beyond measure, not in a hubristic way, not because we're superior, but because we're all there is, the only light in the darkness, the only voice in the silence. Or maybe we're not alone now, but we're the first, the earliest civilization to reach this level of development. The galaxy might be full of pre-technological civilizations, microbes, animals, even intelligent species that haven't developed radio yet, but no one else is at our level yet. We're the pioneers, the first to look up and wonder if anyone else is out there. And the answer, for now, is no, not yet. But someday, maybe millions or billions of years from now, others will follow. They'll reach our level. They'll look up. They'll search. And maybe they'll find evidence of us, our radio signals still propagating through space, our spacecraft drifting through the galaxy, our ruins, if we've colonized other worlds. They'll know they're not alone. They'll know someone else was here before them. They'll inherit a galaxy that we've touched, that we've explored, that we've left our mark on. This possibility is exciting. It means we have a unique opportunity. We could be the elder civilization, the first. We could spread through the galaxy and become the foundation for future civilizations. We could be the ones that others look up to, the ancient ones, the precursors. Or we could leave messages, time capsules, records of our existence, so that future civilizations know they're not alone, know that someone else made it through, that consciousness survived, that the universe has been known before. But it also means we have to survive. If we're the first and we destroy ourselves, we might prevent others from arising. If we colonize the galaxy and then go extinct, we might have altered conditions in ways that make it harder for other civilizations to emerge. We'd be the great filter for everyone else. Our actions have consequences, not just for us, but for the future of intelligence in the galaxy. We need to be careful, thoughtful, responsible. We need to think long term, not just about the next generation or the next century, but about the next million years, about the legacy we leave. So, what should we do? How should we respond to the Fermi Paradox? There are several approaches. First, we should keep searching, keep looking for signals, keep analyzing exoplanet atmospheres for biosignatures, keep searching the solar system for artifacts. The fact that we haven't found anything yet doesn't mean we won't. We've only been seriously looking for a few decades. That's nothing. We need patience. We need better instruments. We need more resources dedicated to the search. Every year, we develop better telescopes, better methods. We catalog more planets. We listen to more frequencies. Eventually, if anyone is out there, we might find them. Second, we should be cautious about broadcasting. The dark forest theory might be paranoid, but it highlights a real risk. We don't know who's listening. We don't know their intentions. Broadcasting our presence might be safe. It might even be beneficial, but it might also be dangerous. Until we know more, we should be careful. We should think carefully about what we broadcast and why. We should have international discussions about whether humanity should actively try to contact aliens or whether we should stay quiet and listen. This isn't a decision for one nation or one organization. It affects all of humanity. We should decide together. Third, we should focus on surviving the great filter, whatever it is. If the filter is ahead of us, we need to get through it. We need to avoid nuclear war. We need to control biological weapons. We need to address climate change. We need to develop AI safely. We need to solve our problems before they destroy us. This is urgent. The next few centuries will determine whether humanity has a future. We're at a critical juncture. The decisions we make now will echo through time. If we succeed, we might spread through the galaxy. We might last for millions of years. We might become one of the great civilizations of the cosmos. But if we fail, we'll just be another extinct species. Another civilization that didn't make it. Another silence in the great silence. Fourth, we should prepare for the possibility that we're alone, or effectively alone because distances are too vast or civilizations are too rare. This means we can't count on anyone else to save us. We can't expect aliens to show up and solve our problems. We're on our own. We have to take responsibility for our own survival, for our own future. We have to be wise stewards of our planet and our civilization. We have to think about sustainability, about long-term survival, about creating a society that can last not just decades, but millennia. That can spread beyond Earth if necessary. That can adapt to changing conditions. That can survive whatever challenges come. Fifth, we should appreciate the beauty and mystery of the question itself. The Fermi Paradox is one of the most profound mysteries we face. It touches on everything: physics, biology, philosophy, sociology, psychology. It asks fundamental questions about existence and meaning and our place in the cosmos. And we don't have the answer yet. We're still searching, still wondering, still hoping. That's exciting. That's what makes us human, the ability to look up at the stars and ask where everyone is, to feel the wonder and the loneliness and the hope all at once, to keep searching even though we haven't found anything yet, to believe that someday, maybe, we might not be alone. The silence might not last forever. Maybe we'll detect a signal tomorrow. Maybe we already have and just haven't recognized it yet. Maybe first contact is coming soon. Or maybe we'll search for centuries and find nothing. Maybe we'll spread through the galaxy and never meet anyone. Maybe we'll always be alone. We don't know. And that uncertainty is what makes the question so compelling. We're living in a time of profound ignorance about one of the most important questions we can ask, and that's okay. That's part of the human condition, not knowing, wondering, searching. The journey toward understanding is as important as the answer itself. Let's delve deeper into what it would mean if we're truly the first technological civilization in the galaxy. This possibility is often overlooked because it seems arrogant, but it's not about superiority, it's about timing. The universe is 13.8 billion years old. Our galaxy is about the same age, but the very early universe wasn't suitable for life. The first stars contained only hydrogen and helium. No heavy elements, no carbon, no oxygen, no iron, nothing needed for rocky planets or complex chemistry. Those elements had to be created in stars and scattered by supernovae. It took time, several generations of stars living and dying before enough heavy elements existed to form planets like Earth. So, there's a minimum age before habitable planets could exist, probably a few billion years into the universe's history. That means life couldn't have started much before about 10 billion years ago. Earth formed 4.5 billion years ago, which is 9.3 billion years after the Big Bang. We're not that late. We're relatively early in the window when complex life is possible, and it took Earth 4 billion years to go from the first microbes to technological civilization. If that's typical, then civilizations arising now would be among the first wave, not the absolute first, but early pioneers. This means we might have an opportunity that later civilizations won't. We could spread through the galaxy before anyone else does. We could establish colonies on thousands or millions of worlds. We could become the dominant civilization, not through conquest, but simply by being first. By the time other civilizations arise, we'd already be everywhere. They'd emerge into a galaxy that's already inhabited, already claimed, already shaped by our presence. This gives us enormous responsibility. How we act now will affect the future of the galaxy. Will we be benevolent? Will we leave room for others? Will we preserve habitats where new civilizations might arise? Or will we be thoughtless and destructive, consuming everything in our path? If we're truly first, we also have the opportunity to shape the future in positive ways. We could leave knowledge caches, databases of information that future civilizations could find. Science, history, philosophy, warnings about dangers we've encountered, advice about challenges we've overcome. We could be mentors to civilizations that arise after us, even if we never meet them face to face. They'd discover our messages and learn from us. They'd know they're not alone. They'd know someone else made it through. They'd have a template for success. Or we could leave something darker, a galaxy full of military installations, automated weapons designed to suppress any emerging civilization that might become a threat, a police state on a galactic scale. This is the terrifying possibility of being first. We get to set the rules, and if we set bad rules, if we create systems of control and oppression, those systems might persist for millions of years. Future civilizations would inherit a galaxy shaped by our worst impulses. They'd be born into a prison we built. This is why our choices matter so much. We're not just deciding our fate. If we're first, we're deciding the fate of the galaxy. Future historians, if they exist, will look back at this moment, the 21st century, the point when humanity became aware of its cosmic significance, when we first seriously contemplated our place in the universe, when we first had to make decisions that affect not just our species, but potentially all future intelligence in our corner of the cosmos. What will they say about us? That we rose to the challenge, or that we failed? Now let's consider another angle on the Fermi Paradox. The problem of recognizing alien life and intelligence when it's fundamentally different from ours. We assume aliens will be biological, carbon-based, breathing oxygen or some other gas, living on planets with liquid water. But these assumptions are based on one example. Us. What if life can be completely different? Silicon-based instead of carbon-based, using liquid methane instead of water, living in the clouds of gas giants instead of on solid surfaces, existing as plasma in the atmospheres of stars. We wouldn't recognize such life if we saw it. We'd classify it as a natural phenomenon. Interesting chemistry. Nothing more. Intelligence could be even more alien. We think of intelligence as residing in brains, centralized organs that process information. But maybe intelligence can be distributed, collective consciousness across millions of small units, like a slime mold or a colony of ants, but scaled up. Each individual unit is simple, but together they form a mind that thinks slowly over days or years, a mind that's spread across a planet or a solar system. How would we detect such intelligence? It wouldn't build radio transmitters. It wouldn't construct spacecraft. It would just exist, thinking its slow thoughts, completely unaware of us even if we're right next to it. Or consider the possibility of intelligence that exists at different timescales. Maybe some minds think much faster than us. What takes us years to think through, they complete in seconds. They'd perceive us as nearly frozen, as effectively inanimate. They might not recognize us as conscious beings because we operate so slowly. Conversely, maybe some minds think much slower than us. What takes them centuries to contemplate, we rush through in minutes. They'd perceive us as mayflies, brief flickers of activity, too fast to track, too ephemeral to matter. They might not recognize us as intelligence because we don't persist long enough from their perspective. These temporal mismatches could prevent communication even if we're in the same location. Imagine trying to have a conversation with someone who thinks 1,000,000 times faster than you. From their perspective, you're taking hours to pronounce a single syllable. They'd get bored and leave long before you finished your sentence. Now imagine the reverse. Someone thinking 1,000,000 times slower. From your perspective, they're taking decades to respond to your greeting. You'd die of old age before the conversation progressed. Communication requires compatible timescales. If aliens think at very different speeds, we might never realize they're intelligent. There's also the question of values and goals. We assume aliens would be curious, that they'd want to explore and communicate. But why? Curiosity is a trait that evolved in humans because it had survival value. Exploring your environment, learning about potential threats and resources, helps you survive and reproduce. But an alien species might evolve in an environment where curiosity is not advantageous, where staying put and not drawing attention is the better strategy. They might have no interest in exploration or communication. They might be perfectly content to stay on their home world, living their lives, completely indifferent to the existence of others. Or their goals might be incomprehensible to us. We value things like survival, reproduction, knowledge, beauty, connection. But these values are products of our evolutionary history. Aliens with a different history might value completely different things we can't even conceive of. They might spend all their time and energy pursuing goals that seem utterly pointless to us. And they might view our goals the same way. We'd talk past each other, unable to find common ground, unable to understand why the other side does what it does. This fundamental alienness might be the real barrier, not distance, not technology, but the sheer incompatibility of minds that evolved under completely different circumstances. We might share the same galaxy, we might even visit the same star systems, but we'd never truly connect because we're too different. We'd be like two species of animal living in the same forest but occupying completely different ecological niches. Aware of each other's existence maybe, but with no meaningful interaction, no communication, no relationship. The anthropic principle also plays a role here. We can only ask questions from our perspective. We're humans on Earth in the early 21st century. We see the universe from this specific vantage point, and from here, the universe looks empty. But maybe that's selection bias. Maybe civilizations can only emerge in conditions that make them feel alone. Maybe the very factors that allow intelligence to develop also isolate it. Rare combinations of circumstances that don't overlap. So every civilization looks around and sees an empty universe, not because others don't exist, but because others exist under conditions so different that contact is impossible. Think about it this way. If the galaxy were crowded with civilizations all in constant contact, would humans have evolved? Maybe not. Maybe intelligence only evolves when a species is isolated, when it has to solve problems on its own, when it can't rely on help from others. So the conditions that create intelligence also create isolation. Every intelligent species emerges alone, looks around, sees no one, and wonders why. The answer is that this is the only way intelligence can emerge. Crowded galaxies don't produce curious civilizations. Only empty galaxies do, or galaxies that seem empty from each civilization's perspective. This is a strange and somewhat disturbing possibility. It suggests that the loneliness we feel when we look at the stars is not an accident. It's a requirement. We're alone because we must be alone, because only in aloneness can intelligence arise. If this is true, then first contact might be impossible by definition. The moment we make contact, the conditions that allowed our existence would be violated. We'd cease to be the kind of beings we are. This sounds like mysticism, but it's a logical possibility given what we know about the anthropic principle and selection effects. Let's also consider the practical problems with SETI. We've been searching for decades, but how thorough has that search been? We've surveyed millions of star systems, but there are hundreds of billions of stars in the galaxy. We've sampled a tiny fraction. We've listened at certain radio frequencies, but the electromagnetic spectrum is vast. We've chosen frequencies we think are likely, the hydrogen line, the water hole, but maybe aliens use completely different frequencies. Maybe they've moved beyond radio entirely. Maybe they use optical laser communication, or neutrino beams, or something we haven't thought of. We've also only been listening continuously for a short time. Radio signals from a civilization 50 light years away take 50 years to reach us. If they sent a signal 50 years ago but stopped broadcasting 49 years ago, we'd miss it. We wouldn't be listening yet when it passed through our solar system. Timing matters. We need to be looking at the right place, at the right time, in the right way. The odds of all those factors aligning are small, so the fact that we haven't found anything yet doesn't mean much. We need to keep looking, longer, more thoroughly, with better instruments. There's also the matter of what contact would actually look like if it happened. We imagine receiving a clear signal, a message in a format we can decode, maybe mathematical patterns, maybe images, maybe something deliberately designed to be understood by any technological civilization. But real contact might be much messier. We might receive signals that we recognize as artificial but can't decode. Signals that clearly contain information but in a format completely alien to us. How do you decode a message when you don't know the language, the symbols, the underlying concepts, or even the basic structure of how information is organized? Decoding an alien message would be like an archaeologist trying to read Linear A, the undeciphered Minoan script. We have texts in Linear A. We know it's writing, but we can't read it. We don't know what language it represents. We don't have a Rosetta Stone to help us. It might be forever undecipherable. Now imagine that problem scaled up to an alien civilization. Not just a different language and alphabet, but different concepts, different logic, different ways of organizing thought. The message might contain profound wisdom, the secrets of the universe, solutions to all our problems. But if we can't decode it, it might as well be random noise. Some researchers have worked on creating messages that would be universally decodable. The Arecibo message sent in 1974, the Voyager Golden Record. Pioneer plaques. These use simple symbols and mathematical concepts that presumably any technological civilization would understand. But we don't know if that's true. We're assuming aliens think like us, that they use the same mathematics, the same logic, the same way of representing information. Maybe they don't. Maybe their mathematics is so different that our diagrams mean nothing to them. Or maybe they're much smarter than us and our messages seem childishly simplistic. Either way, contact might not lead to understanding. There's also the question of what we do if we detected a signal. This is something SETI protocols address. If we receive a confirmed artificial signal from space, what's the procedure? First, verify it. Make sure it's not a mistake or a hoax. Get multiple observations. Confirm it's coming from space and not from Earth. Second, determine what information it contains. Try to decode it. Figure out what they're saying, if anything. Third, decide how to respond. This is the controversial part. Do we respond? Who decides? One government? The UN? All of humanity somehow? What do we say? Do we reveal our location and capabilities? Or do we stay quiet and just listen? These are profound questions without clear answers. Different people have different opinions. Some think we should respond immediately, make contact, begin a dialogue. The potential benefits outweigh the risks. We could learn so much. Technology, science, philosophy, solutions to our problems, friendship across the stars. Others think we should be cautious. Observe but don't respond. Learn what we can without revealing ourselves, because we don't know their intentions. Contact could be dangerous, maybe even fatal. Stephen Hawking, as mentioned, was in this cautious camp. He warned that aliens might view us as resources to be exploited. That contact could go badly. History offers some uncomfortable parallels. When technologically advanced civilizations on Earth encountered less advanced ones, it usually went badly for the less advanced. Colonization, exploitation, disease, cultural destruction. The indigenous peoples of the Americas, of Australia, of Africa. When Europeans arrived with superior technology, the natives suffered enormously. Millions died from disease alone, many more from violence and exploitation. Their cultures were destroyed or marginalized. Their lands were taken. They were treated as inferior, as obstacles to be removed or resources to be used. If aliens are even slightly more advanced than us, we might be in the position of indigenous peoples facing colonizers. The power imbalance could be catastrophic, but this analogy might not hold. Interstellar distances are vast. Physical colonization of Earth might not be practical or desirable for aliens. They might have no interest in our planet or our resources. Everything they need might be available closer to home or in uninhabited systems. So the colonial model might not apply. Contact might be purely informational, an exchange of ideas and knowledge with no physical interaction. That seems safer, though even information can be dangerous if used unwisely. Another consideration is the impact contact would have on human society. Finding out we're not alone would be psychologically and culturally transformative. Every religion would have to grapple with the existence of alien life. Every philosophy would need to expand its scope. Every government would need to consider humanity's place in a populated cosmos. It would be the biggest revelation in human history, more significant than any scientific discovery, more impactful than any political or social change. The world after contact would be completely different from the world before. Some people would find this exhilarating, proof that we're not alone, that consciousness exists elsewhere, that the universe is full of minds and civilizations. It would give us hope, show us that survival is possible, that intelligence has a future, that we're part of something larger. Others would find it terrifying. The unknown is scary. Aliens are unknown. What do they want? What can they do? Are we safe? The uncertainty would create anxiety. Some people would panic. Some governments might try to suppress the information to prevent social upheaval. But in the modern world, information spreads too quickly. You can't keep something like alien contact secret for long. Too many people would know. Too many observations would confirm it. There's also the religious and philosophical impact. Many religions are anthropocentric, focused on humanity's relationship with the divine. The idea that God created humans in his image, that Earth is special, that humanity has a unique covenant or destiny. Alien life challenges these ideas. If God created aliens too, are they also made in his image? Do they have souls? Do they need salvation? Different religions would answer differently. Some might embrace aliens as part of God's creation. Others might reject them as demons or deceptions. Still others might schism over the question. Religious leaders would need to provide guidance, but different leaders would give different guidance. It could be divisive. Philosophically, alien contact would force us to reconsider what it means to be human. What's special about us? What's unique? Intelligence? No, aliens have that too. Consciousness? They probably have that. Tool use? Culture? Language? If aliens have all the traits we think make us special, then what distinguishes us? Maybe nothing. Maybe we're just one type of mind among many, one way of being conscious among countless ways. That's humbling, but also beautiful. It means consciousness and intelligence are not accidents. They're not unique to Earth. They're features of the universe, properties that emerge wherever conditions allow. That's profound. The practical implications of contact would also be enormous. If we receive information from an advanced civilization, we might gain technologies that leapfrog our development. Fusion power, faster than light travel. Nanotechnology, life extension. Solutions to disease and aging. Solutions to climate change and resource scarcity. This would be incredibly beneficial. It could usher in a golden age, but it could also be destabilizing. Economic systems based on scarcity might collapse. Political power structures might shift. Inequality might increase if some people or nations gain access to alien technology before others. We'd need to manage the transition carefully, share the benefits broadly, avoid creating new conflicts. There's also the possibility that alien information could be harmful, not intentionally. They might not mean to hurt us, but information can be dangerous if misapplied. Instructions for building powerful weapons, nanotechnology that could be weaponized, biological knowledge that could be used to create pandemics, or even information that's so paradigm-shifting that it destabilizes society. Imagine if aliens casually mentioned that consciousness is an illusion, that free will doesn't exist, that everything you experience is just brain chemistry with no deeper meaning. Even if true, that knowledge could be psychologically devastating to many people. It could undermine motivation, morality, meaning. We might not be ready for certain truths. This raises the question of whether aliens would deliberately send information that's harmful. Maybe not directly, but they might include knowledge that's dangerous if used incorrectly. A test to see if we're wise enough to handle it, or they might not think about it at all. They might assume we're sophisticated enough to use information responsibly, or they might not care. They're just broadcasting everything they know, and it's our problem if we misuse it. There's no guarantee that contact would be benevolent. Even well-meaning aliens might accidentally harm us through cultural or technological contamination. All of this assumes aliens would want to communicate at all. Maybe they don't. Maybe they've concluded that communication across interstellar distances is pointless. The time delays are too long. The chance of misunderstanding is too high. The risk of conflict is too great. So they don't bother. They live their lives, pursue their goals, and ignore the rest of the universe. This would explain the silence perfectly. Civilizations exist, they're common, but they're all introverted, focused inward, uninterested in contact. We're shouting into a cosmos full of civilizations that have chosen not to listen or respond. Or maybe communication requires reaching a certain level of technological and social development. Maybe there's a threshold, a point where a civilization matures enough to join the galactic community. Before that threshold, you're quarantined, ignored, left alone to develop. After you cross it, you're welcomed, given access to the network, taught the protocols. But we haven't crossed it yet. We're still too primitive, too violent, too divided. When we achieve global peace or develop faster than light travel or demonstrate some other milestone, then we'll be contacted, not before. This is similar to the zoo hypothesis, but with a specific trigger condition. What might that trigger be? Some possibilities: achieving lasting peace on Earth, demonstrating we can manage our planet sustainably without destroying it, developing technology that proves we're capable of interstellar travel, solving internal conflicts so we present a unified species rather than competing nations, showing ethical maturity by how we treat our own environment and species. Any of these might be criteria, or something else entirely, something we haven't thought of, a test we don't know we're taking. And we'll only know we've passed when contact happens. The silence might also be temporary. Maybe civilizations go through phases. Early on, they broadcast. They're excited. They want to make contact. But after centuries of silence, they give up. They stop broadcasting. They turn inward. But they keep listening, just in case. We might be in that silent phase. All the civilizations out there gave up on SETI decades or centuries or millennia ago. They're listening, but not broadcasting, waiting for someone else to speak first. Everyone, waiting for everyone else. So the silence persists, even though many civilizations exist. We're all listening, no one's talking. If we could all agree to broadcast simultaneously, we'd all detect each other. But coordination is impossible without communication. So we remain isolated. This suggests a strategy. Keep broadcasting, even if we don't hear anything back, even if it seems futile, because someone might be listening. They might not respond immediately, but years or decades or centuries later, they might. Our signal would take time to reach them. Their response would take time to reach us. Patience is required. We need to think in terms of generations. We might not see the response in our lifetimes. Our children might not, but our descendants could. The conversation would span centuries. but it would be a conversation. Ultimately, the Fermi Paradox teaches us about uncertainty, about humility, about the limits of our knowledge. We don't know why the universe seems empty. We have theories, dozens of them, each plausible, each with strengths and weaknesses, but no definitive answer. And that's okay. Science is about asking questions and seeking answers. Sometimes the questions persist for decades or centuries before we find answers. Sometimes we never find answers. We just refine the questions, make them more precise, develop better tools for investigating them. The Fermi Paradox is one of those enduring mysteries. It might be solved tomorrow if we detect a signal, or it might remain unsolved for generations. Either way, the pursuit of understanding is valuable in itself. The paradox also teaches us about perspective, about how our assumptions shape what we see. We assume aliens would be like us in certain ways, curious, technological, communicative. But maybe they're not. Maybe they're so different that our assumptions break down. Recognizing this helps us think more flexibly, more creatively. It pushes us to consider possibilities we'd otherwise dismiss. This is valuable not just for understanding aliens, but for understanding ourselves. By imagining the alien, we see ourselves more clearly. We see which traits are universal and which are contingent, which aspects of humanity are fundamental to intelligence, and which are accidents of our particular evolutionary path. The search for aliens is also the search for meaning, for connection, for an answer to the question of whether we're alone. This question is deeply human. We're social creatures. We form communities. We seek connection. The idea of being alone in the universe is existentially troubling. It contradicts our nature. We want to believe there are others out there. That consciousness is not a fluke. That intelligence has a future. That we're part of a larger community of minds scattered across the cosmos. Even if we never meet them, even if the distances are too vast. Just knowing they exist would change how we see ourselves and our place in the universe. And if we are alone, if the search continues for centuries and we find nothing, that too would be meaningful. It would tell us we're rare, perhaps unique, that consciousness and intelligence are precious, that we have a responsibility to preserve and protect them, that our choices matter not just for us, but for the cosmos, because we might be all there is, the only voices in the silence, the only light in the darkness. That's a heavy responsibility, but also an honor, to be the universe's way of knowing itself, of appreciating its own beauty and complexity. If we're alone, then what we do matters more, not less. The silence might not last forever. Maybe we'll detect a signal tomorrow. Maybe we already have and just haven't recognized it yet. Maybe first contact is coming soon. Or maybe we'll search for centuries and find nothing. Maybe we'll spread through the galaxy and never meet anyone. Maybe we'll always be alone. We don't know. And that uncertainty is what makes the question so compelling. We're living in a time of profound ignorance about one of the most important questions we can ask. And that's okay. That's part of the human condition, not knowing, wondering, searching. The journey toward understanding is as important as the answer itself. Thank you for exploring the Fermi Paradox with me. If this changed how you think about our place in the universe, a like or subscribe really helps keep this channel exploring these profound questions. And remember, whether we're alone or not, whether aliens exist or don't, whether they're hiding or extinct or just too far away, we're here, we're conscious, we're asking the questions, we're looking at the stars with wonder. That's extraordinary, that's precious, that's worth protecting. The universe might be silent, but we're not. We're the voice in the darkness, the light in the void, the question mark in the cosmic equation. And as long as we keep asking, keep searching, keep wondering, the silence isn't quite so empty. Good night, and may the search continue.